Good time of day, dear colleagues, and welcome to our next session of the research methods in psychology course. Today we are going to discuss finally statistics, and we'll start with the most basic statistics that involve just one or at the maximum two samples. The topics that we are going to discuss today. First of all, we'll take a look at the procedures that we can use for data cleaning to make sure that our data don't contain any strange, abnormal observations. And then we'll discuss a little bit the general principles of the choice of statistical methods that we can apply. And then we'll take a look at different statistical tests. We'll start with the most basic tests that only involve a single sample. And then we'll take a look for tests that involve two or more samples, and I will take a look also at the measures of association between a couple of variables. And finally, we'll discuss how can we present the results of our statistical analysis in APA style. And this is the style that we will be asking you to present your data in for your home assignments, just to give you a little bit of chance to practice with APA style. And we'll also discuss a little bit, as a kind of bonus track of today's session, the ways we can deal with missing data and the types of missing data that we can encounter. So our goal during this discussion will be to understand the general principles of quantitative data analysis using different statistical methods that we can apply. And that's why our discussion in this lecture is going to be mainly theoretical, because you might want to apply completely different statistical packages for your actual analysis, and different seminar groups might actually be using different packages at the same time. There are quite a few tools available on the market, so to say. There are well-known packages of previous generation. These are mainly commercial packages like the SPSS, and most universities provide access to SPSS, but if you don't, there is Statistica, which costs very little. Some large companies use SAS, and there are many other options. But there are also competitors of a newer generation. These are packages that are completely free of charge, and initially they were somewhat more limited in their capabilities, but now they are very rapidly catching up. Of course, the most important development was the development of R statistics, which is essentially a programming language which does not contain any graphic interface by default. But based on R, we have seen the development of two other packages. There is JASP, or JASP, that we've discussed last time when we took a look at Bayesian data analysis, because JASP is very strong in this respect. But there is also another package that I can completely recommend to anyone who is just starting to learn statistics. It's called Jamovi. It is also based on R. It's very similar to JASP. Essentially, it was developed by the same team, and then it was forked. But Jamovi, it tries to mimic SPSS in its graphic interface. So it's very intuitive, it's very simple to learn, and another great advantage is that it provides you the tables in APA style, which saves a lot of time and effort. But we'll discuss those things today. So regardless of what kind of package you're actually using, the general principles will stay the same, and in our discussion in this lecture, we'll mainly focus on the general principles. So here it comes, the Trojan horse of statistics. Please open your gates wide, the gates of your brain, and prepare yourselves to be captivated by this bunch of statistical criteria. So our first topic for today is data cleaning. What is data cleaning, and why do we even need to clean our data? Well, because in many cases we might have unexpected problems. For example, we are typing our data into an Excel sheet, and at some point a key on our keyboard doesn't work, and then instead of two numbers 5 and 5, we type a single number 55, and obviously this is a very abnormal value. Sometimes also we have missing data codes. Different types of missing data might be coded with different values, like -9 or -99. And if our statistical package does not know that this particular value is used to code missing data, we might encounter all kinds of strange results as a result of our analysis. That's why before you actually start applying any complex statistical criteria to your precious data, it makes sense to always start with a calculation of descriptive statistics to make sure what kind of data we have, if the properties of this data are in order the way we expect them to be. And also at this stage, we try to find some abnormal data, some abnormal observations that might violate our assumptions. And also we use this information that we obtain at this stage in order to evaluate distributions of our variables, which is essential in order to choose properly our statistical tests. And also at this stage, we are trying to figure out how much missing data we have and what are the reasons for this missing data. So we'll discuss this issue a little bit separately because it's slightly more complicated. But right now, we'll start with descriptive statistics. Why on earth do we even need them? Because descriptive statistics give us the most basic information about our data, which is necessary to understand whether these data are correct and what kind of statistical tools we can use to analyze it. Among the descriptive statistics that we need, the most important ones are, of course, mean and standard deviation. But in addition to mean, we can use also other measures of central tendency, this parameter is also called distribution location. Where is your distribution located on this horizontal axis? Where is its center? And we have at least 3 different statistics that we can use here. The mean, which is basically the arithmetic mean or the average of all values in your sample. There is also median. Median is a point in your distribution that separates 50% of individuals with lower values or scores and 50% of individuals with higher values or scores. And a third central tendency statistic that can sometimes be useful is called mode. Mode is basically, just like the word mode suggests, is the most frequent, the most widely spread value in your sample, the most frequent score that you encounter. Why do we need 3? Well, because sometimes we have strange distributions like this. For variables like income, this distribution might have a heavy tail at one end, because obviously there are most people receive fairly small incomes, but there is also a substantial proportion of individuals with fairly high incomes. That's why if you calculate a mean score, it will be somewhat biased to the right. It will be inflated by this group of observations on the right. But a median, which basically separates 50% of observations with lower and higher scores, will give you a much more realistic estimate of how your data are distributed. That's why in the States, when they report on salary, they normally present median, and in Russia, they normally publish the mean, because it is larger. Of course, if your distribution is normal, it is perfectly symmetrical, and mean, median, and mode are going to be the same. They will have the same value. So already, if you see that mode, median, and the mean have the same value, it suggests that probably this distribution, if not normal, it is at least symmetrical. And if you see strong differences between the mean and the median, this already suggests that maybe this distribution, maybe there is something potentially wrong with it. Another bunch of descriptive statistics that we can apply are the statistics of variability. In R, this parameter of distribution is also called scale. These are statistics that describe how widely or how narrowly spread are our observations around the center of our distribution. And we discussed a little bit earlier standard deviation, which is the most common statistic in this group. Variance is basically pretty much the same, but it's squared. That's why it's not so convenient. So if you're measuring variability of, for example, people's height measured in centimeters, variance will be expressed in square centimeters because it's squared, and standard deviation will be expressed in your original units. That's why it's more easily interpretable. But there are also additional statistics that we can use. For non-parametric variables, where distribution is very strange, it's not normal at all, standard deviation might not describe it very well, because it will be also biased by abnormal observations at the ends of your distribution. That's why for distributions that are not normal, more often we tend to use what is called quartile range. Quartiles are points that separate 25%, 50%, and 75% of all observations on your distribution. So we use the point which corresponds to lower quartile and the point which corresponds to higher quartile. And we calculate the difference between the two. And this way we can describe any distribution, even if it's not very normal. And another statistic which is extremely useful is called range. It's basically the difference between minimum and maximum value. Whenever you're calculating descriptive stats, just be sure to enable minimum and maximum, because these are two statistics that can tell you if there are some abnormal data values, if there are some data entry errors that fall out of range of normal values. For example, if you have for an item a response scale which goes from 1 to 5, and you see the value of 55 is the maximum for this variable, obviously there is a mistake somewhere, and you need to correct this mistake before you actually start analyzing your data. Unfortunately, the bad news are that mean and standard deviation are not enough for us to describe a distribution well. As an illustration, there is this classical data set which was created by a mathematician called Francis Anscombe, and it's called Anscombe's quartet. These are 4 different data sets. Each of them has 10 observations, and these 4 data sets have exactly the same statistical properties. They have the same mean, they have the same variance for both variables, hence the same standard deviations. The correlation between 2 variables is also the same. However, if you take a look at those scatter plots, you see that they are vastly different, that these data sets are substantially different, even though they share the same statistical properties. And that's the reason why Francis Anscombe created them, to illustrate the importance of looking at your data, of inspecting your scatter plots before you actually start your analysis. And that's also why we need a couple of other statistics to describe our distributions. 2 more statistics that are extremely useful are skewness and kurtosis. We discussed a little bit before, and you might remember that skewness and kurtosis for a normal distribution, they are equal to exactly 0, and skewness describes whether our distribution is symmetrical or not, and in which direction it is skewed, and kurtosis describes whether it's narrow or it's kind of flat compared to normal distribution. And just like any other statistic, these statistics also have standard errors. Depending on your sample size, you might estimate skewness and kurtosis more or less precisely. And you can use these standard errors in order to formulate hypotheses whether your distribution is normal or not. Basically, just like for any statistic, standard errors reflect the expected standard deviation of this statistic in different samples of this size. So if you take skewness and kurtosis, and if you divide skewness and kurtosis by their respective standard errors, what you get is essentially a z-score. And it tells you what is your chance of obtaining this or more abnormal value for skewness and kurtosis, assuming that it is 0 in the general population. So as a rule of thumb, if skewness and kurtosis values are more than twice over their standard errors, this suggests that there is only 1 in 20 chance of observing such strong values of skewness and kurtosis by chance alone. So it's a potential indication that these data might be not normal. However, there is a bit of a problem, because even in very large samples, even very small values of skewness and kurtosis might be statistically significant, because standard errors are going to be very small. That's why this approach is not extremely helpful, but as a rule of thumb, sometimes it can be useful. So what do skewness and kurtosis tell us about this Anscombe quartet? And here there are 3 comments that you can use in R. Datasets double semicolon Anscombe loads this Anscombe quartet, which is one of the basic datasets in R. Then we load library psych, and we use its function describe to get descriptive statistics in an extremely convenient format. And here, for each of these 4 samples, you see descriptive statistics for x and for y variables. And you see that skewness and kurtosis values are fairly pronounced. In most cases, they are above 1 or below -1, suggesting that these distributions are not normal and there is something going on with them. However, what exactly is going on with them, it's hard to say just by looking at those values. Of course, scatter plots are much more informative. So how can we tell if our distribution is normal or not? Probably the best approach is to use graphical methods. You can plot in any statistical package a histogram with a normal curve, and you will see if your observations fit neatly under this curve or there are some abnormalities. You can also use scatter plots. In R, it's very convenient. There is also the normal range on the scatter plot. Or you can use dedicated plots like probability or quartile plots, PP and QQ, available in SPSS, which let you very easily kind of have an idea of whether your distribution is normal or not. However, you can also look at skewness and kurtosis values. Basically, skewness and kurtosis values are effect sizes for the deviation from normality of your distribution. So if they are kind of small, if they are within the range from -1 to 1, probably there is no need to worry very much about your normality. And even some methodologists suggest that if skewness and kurtosis are within the range of -2 to 2, this distribution can be deemed approximately normal, and you can kind of use methods that assume normal distribution without much bias. Of course, there are also statistical tests available that can tell us whether our distribution is normal or not. The most familiar in Russia is Kolmogorov-Smirnov test, but there is also Shapiro-Wilk and others newer statistical approaches. These tests basically test NH0 hypothesis that your observed distribution equals expected normal distribution, that your sample comes from a population with a normal distribution, and hence, if the value of Kolmogorov-Smirnov test or Shapiro-Wilk's test is significant, it means that the chance of seeing this distribution in your sample, in case it comes from a normally distributed population, is actually very small. So if p-value is significant, we say this distribution is probably not normal. However, these statistical tests, they have limited applicability. Because if you have very large samples, obviously these statistical tests will be able to detect very small and very trivial deviations from normality that will not have any implications for your analysis. And on the contrary, if your sample is very small, about 30 observations or less as a rule of thumb, probably these tests will not be powerful enough. Even if your deviation from normality is quite substantial, it will not be possible to say that it is statistically significant just because your sample is very small. That's why in small samples, it's very difficult to tell if your distribution is normal. So not personally, I don't really use those statistical criteria. I just look at skewness and kurtosis values, and if they are within the range from -1 to 1, I don't worry. And if they are within the range of -2 to 2, I kind of proceed with methods that assume normality, but carefully. But what can we do if our distribution is not normal? There are different reasons and different ways to kind of resolve this issue. First of all, maybe there are some abnormal data points. some outliers with extremely high or extremely low values that kind of bias your distribution. The second potential line of reasoning is this distribution actually supposed to be normal? We know that for some variables, it's almost never perfectly normal. For example, when we measure well-being and happiness, we usually see that most people have scores in the higher range. They say we are fairly happy or very happy, and there are few people who say that we are unhappy and we suffer. And this is always the case in developed countries, so you can never obtain a perfectly normal distribution. Or if you are dealing with some physiological variables, their distribution is often logarithmic. So you need to, instead of searching for outliers, maybe it makes sense to transform the data. Or you can use some robust or non-parametric statistics. And we'll discuss those issues now very quickly. If you're thinking about outliers, what are outliers? These are individual data points that are substantially different, that correspond to units, to individuals who are substantially different from the rest of your sample. And that's why if all the data points are like a nice, neat circle on your scatter plot, this individual data point is like a single capricious bird that flew away from its flock. And of course, you can detect it. The easy situation is when this outlier is only on a single variable. Then you can easily detect it. But there are also more complicated situations when an outlier is multivariate, when on every single variable it appears to be within the normal range, but based on a combination of variables, this point is definitely anomalous. How can you detect outliers? Well, for univariate outliers, it's very simple. You can just convert your data to z-scores, standardize your data. And basically, z-score for each individual data point corresponds to probability of finding this data point in a sample. Normally, the cutoff for outliers are z-scores above 3 or below -3. These are kind of suspicious data points. But of course, if your sample is very large, you can still find points like this just by chance alone. If you have more than 1,000 individuals, probably you'll see several data points that are outside the 3 or -3 range, just as a result of normal probability. But data points with z-scores above 4 or 5 are of course very suspicious, because the probability of finding them by chance is very low. However, if your distribution is asymmetrical based on the properties of what you are measuring, this criterion might need to be adjusted. And if you remove such observations, your distribution normally becomes closer to normal. Your values of skewness and kurtosis might come within an acceptable range. However, whenever you remove any data points from your sample, you always need to justify it, first of all, to find an explanation. Why is this data point different from all the other observations? What is wrong with this individual? Of course, when you present your research report, you need to mention that you performed data cleaning and that you excluded some data points. Nowadays, this kind of data cleaning is not considered a very good practice, because people realize that it gives researchers additional degrees of freedom to manipulate their data. That's why I don't really clean my data much. However, just to have an idea of what we can do, another type of outliers are multivariate outliers. So imagine a point that for every individual variable it might lie within the acceptable normal range, more or less, but based on a combination of variables, it is away from this circle in this multidimensional space. And you cannot detect it by just converting your data to z-scores, but you can calculate special statistics that basically reflect the distances of each data point from all the other data points taken together. The most commonly used measure is Mahalanobis distance, after an Indian mathematician, Mahalanobis. and it can be easily calculated in SPSS in the regression module. Imagine that you have 30 questions in your questionnaire, and you're trying to detect individuals who produced very abnormal response patterns. You can include in SPSS in regression any dependent variable, just the number of observation or an empty column. And all of the variables you're interested in, you include as predictors. And in options, you request Mahalanobis distance. And as a result, for every individual data point, you will see a value. If this value is very large, it suggests that this data point is very much away from all the other data points. And you can also evaluate this value statistically using a table of critical values of chi-square distribution. So if in your questionnaire there are 30 questions which you use to calculate this Mahalanobis distance, you need to take a critical value for 29 degrees of freedom, the number of your variables -1, and probably it makes sense to use a very conservative criterion, so I would use 58.3 as the minimum value above which I would consider my data points to be potential outliers. However, again, this approach is definitely not perfect because it assumes multivariate normal distribution, and if your distribution is not normal, you might get some data points with values that will be outside this expected range. But that does not mean they are outliers. It basically means that your distribution is not so normal. That's why nowadays people don't really clean outliers very much. However, it makes sense to do it just to screen for data errors. Another possibility is that the actual distribution of your data is supposed to be not normal. For example, in economics, if you measure people's income, you will typically find this logarithmic distribution or log normal distribution. And you need to apply a logarithm function to make it normal. The same situation can be found with many physiological measures. For example, electromyogram, when you measure the voltage, or skin conductance, galvanic skin response. These types of measurements also produce log normal distributions that are not supposed to be perfectly normal. And then you're supposed to apply some kind of transformation to make it normal to be able to deal with it. And in Tabachnik and Fiedl's book, there are some suggestions that of potential transformations that you can apply. Or there are some more universal transformations like Box-Cox transformation or optimal scaling that are trying to kind of adjust the points on your scale to make this distribution more normally shaped. However, when we apply these transformations, we need to do it very carefully because they are nonlinear transformations that can change substantially the properties of our data. If your scale was initially ordinal, it does not really matter. Your interpretation will still be pretty much the same. However, if your scale was initially interval and you applied some kind of logarithmic transformation, you need to be aware that now your interpretation of all associations, it does not apply to your original units, but to the logarithm of those original units, and so on. That's why we need to use these transformations with care. In some research areas, like economics, people use them a lot. In psychology, in psychometrics, we normally tend to have already fairly normal distributions, so we rarely apply it. But in physiological, with physiological measurements, still we transform our data. So whenever you choose it, use with care. And of course, our data might have some other possible, so to say, problems if they violate assumptions of our statistical tests. But we'll learn how to deal with those assumptions a little bit later on. Barbara Tabachnik and Linda Fiedel proposed to us a little checklist of the things that we can do when we start looking at our data. But first of all, of course, calculate your descriptive statistics, check for any values that are potentially out of range, that are strangely high or strangely low, check for univariate outliers, check out your missing data if you have any, and why and what are you going to do with it. And if you're planning to apply some multivariate tests, it makes sense to also check for multivariate outliers or linearity of your associations and so on. Okay, so this was a little summary of data cleaning. And if you are interested in dealing with missing data, there is a separate discussion at the end of today's lecture. So now you have cleaned your data and you need to start your actual analysis.